Hello again. In the previous section, we learned how to solve a couple of important problems by using a process where we took an input and got it closer and closer to a specific value. This is called a limiting process. In this section, we're going to learn more about the limiting process. We're going to introduce some notation for it and see when we can find limits and some situations where we can't. So suppose we're given an expression. If we allow the input to get very close, what does that mean? Get very close. If we allow the input to get very close to a specific value and see what happens to the output of the expression, we're using a limit process. Now I said get very close. What does that mean? So you might have an intuitive understanding of what it means to get very close, but to a mathematician, that intuitive understanding is very different from a precise definition. We're not going to worry so much about the precise definition in this course. Now, if you're a math major, you're going to take an advanced calculus course where you're going to have to deal with that precise definition. But for our purposes, we're not going to worry too much about that. All right, so the notation. Here's what the notation is. Here's what we'll say. The notation looks like this. LIM, that's the limit, as the input, I'll use x for the input, approaches some value a of some function is L. All right, so this is the notation we use for the limit. All right, so what we understand from this, the limit of f of x, of the function, as x, the input, approaches a, is L, whatever that is. All right, so we're letting our input, right? X is the input, and we're letting it get close to some specific value on the function, and it gives us some output, if it exists. We'll talk more about what we mean if it exists. So now here's an imprecise definition. We can make the function f of x get as close to L as we want, provided x is sufficiently close to a but not equal to a. So the imprecise definition of the limit, if this limit exists, if this thing exists, what it means is we can make the function get as close as we want to a specific value, a specific output, by letting the input get sufficiently close to some specific value, but not necessarily equal to that value. So what we're going to learn in this section is some numerical and graphical methods for approximating limits, and in later sections we will learn some actual analytical techniques that we can use to evaluate limits. Analytical meaning using algebra, using trigonometry, using those techniques rather than using a calculator. All right, so let's see an example. So here we're asked to use a table of values to find the limit, and the notation we have is the limit as x approaches 3 of, here's the function, x squared plus x minus 12 over x minus 3. Now notice, I can't just let x equal 3. If you look at this really quick, you can see that if I let x equal 3, the denominator turns into a 0. And we know that that's an undefined expression. In fact, it's even worse. If I let x equal 3, notice in the numerator I've got 3 squared, which is 9, plus 3, which is 12. 12 minus 12 is 0. In fact, I have an expression 0 divided by 0. What we'll say later is this is called an indeterminate form. That's even worse than undefined. So what we're going to do is not let x equal 3, but let x get very close to 3. So let's think about the number line for a moment. Here's my number line, and here's 3. What I want to do is I want to take x values. I want x to take values that are greater than 3 and get very close to 3. And I want x to take values that are less than 3 and get close to 3. And see what happens. So what are some values, right? Think about this. What would be values that are close to 3 but on the right of 3? Maybe 3.1. That's pretty close to 3. Maybe 3.01. That's even closer to 3. Maybe 3.001. Or 3.0001. Okay, now what about on the other side of 3? Maybe 2.9. And then 2.99. And then 2.999. These are numbers that are close to 3, but not equal to 3. Okay, so let's see how we can do this on our calculator. Alright, so I bring up my calculator, and what I'm going to do is I'm going to just directly input this function, the x squared plus x minus 12 over x minus 3, in my y equals screen. So I go to my y equals screen, and I'm going to need parentheses around the numerator and parentheses around the denominator. You always got to be careful about that with these rational expressions. So parentheses, x squared plus x minus 12. There's the numerator. Division. And now for the denominator, parentheses, x minus 3. Close that off. I'll hit enter. That's my y1. Now, I'm going to go to my table settings. I'm going to be inputting various numbers getting close to 3, so I don't want to have a necessary start and change in table because it's not consistent. The change in the x is not consistent. Instead, I want the independent line to read ask. Alright, so let me go to the table. And I've got some stuff in there from a previous exercise. Alright, so now let's look on the left first. So let's start at 2.9. And then let's go to 2.99 and hit enter. And 2.999. Let's do one more. 2.9999. All right, let me drag that over here. All right, so I'd say that this is evidence. All right, as x was approaching, so notice what's happening here is my x values are approaching 3. All right, these values approach 3. My y values, what's happening to my y values? As the x values are approaching 3, the y values appear to be approaching approaching 7. Now, we're not done though. We have to check the other side. All right, so let's go back to our table. Let's delete the old stuff. And now let's move in from the right. Let's go to 3.1, 3.01, 3.001, and just to be equivalent on the other side, 3.0001. All right, and again, what I see is my x values approaching 3 and my output values approaching 7. This is evidence, this is numerical evidence, that this limit, that the limit as x approaches 3 of x squared plus x minus 12 over x minus 3, this appears to be 7. So that's the idea that we can use to estimate the limit of a function numerically. We let our x values get closer and closer, and we use a calculator to calculate the various outputs. And if those outputs appear to be getting closer and closer to the same value, we can use that as an estimate of the limit. So here's a couple of exercises. I'd like for you to try these on your own using your calculator. Now, one thing to be careful about in the second exercise here is we have a sine function, sine of pi x over x minus 2. Be careful here. Make sure your calculator is in the correct mode. We assume radian mode unless we are told otherwise in calculus. All right, so here's a couple of exercises. Now would be a good time to pause. Try these out on your own. Did you pause? Did you try these on your own? I hope you did. All right, so let's think about this. If x is approaching 1, if I think of my number line, think about numbers that are getting closer to 1 on either side. 0.9, 0.99, etc. 1.1, 1.01, etc. Let's go to my calculator. Y equals screen. Clear that off. The numerator is x squared minus 1. The denominator is, that should be an x squared. That numerator should be an x squared. Sorry about that. Alright, so that should have been an x squared. Pause now and try this one again on your own. Alright, so x squared plus 3x minus 4. Alright, so now let's go to my table. Let's clear out the old stuff. Let's see. Let's start with 0.9, 0.99, 0.999. Alright. I could do more values if I wanted, but let me move to the other side. Let's go with 1.001, 1.01, and 1.1. All right, so looking at this evidence, right, we're getting close to 1. But not equal to 1, my outputs appear to be getting close to 0.4. I would say that this limit appears to be 0.4. Let's look at the next exercise. Limit with x approaching 2 of sine pi x over x minus 2. Let's clear out the old stuff. Sine pi x. Divide that by the quantity x minus 2. Clear out the old table. Oh, let me check my mode. I'm in degree mode. Let's switch it to radians and hit enter. I almost got caught in the common error. All right, so sine pi x, I've got the function in, and let's see. So letting x approach 2. Let's go with 1.9 as an input. 1.99. 1.999. 2.001. 2.01. 2.1. All right, let's look at these. Let's look at this information. All right, my inputs are getting close to 2. My outputs are getting close to 3.1416. Now, hopefully you recognize that number. Let's see. Now, one thing to be aware of is that if you actually move your cursor over that value, it shows more decimal places. So one thing to be aware of on these tables is it will round to, I guess, 4 decimal places here in the table. But if you actually put your cursor over it, it shows more. And so what I see here is 3.14159, right? If we were rounding, I recognize that to be approximately pi. So these numbers appear to be approaching pi. All right, try the next one. The limit with x approaching 4 of the absolute value of x minus 4 over x minus 4. Now, if you're not aware of it, on the calculator, the absolute value can be found under the math menu and one place to the right. There's the absolute value. So if I'm just on my home screen, if I go math to the right to num for numbers, hit enter, the absolute value of -9 is, of course, 9. All right, so try that exercise out on your calculator. The limit. Try to find that limit on your calculator. All right, so let me go back to my y equals screen. And I'll clear out the old stuff. Let's bring up the absolute value. Math, right, absolute value of x minus 4. And I'm going to then divide that by x minus 4. Oh, need parentheses. All right, and let me go to my table and delete the other stuff. All right, now if I'm going to let x approach 4, how about we use 3.9 as an input, 3.99 as an input, 3.999. That's nice. -1s. Consistent. Okay, now let's look at the right-hand side. 4.001. 4.01. 4.1. Hold on now, these aren't the same. See, something different's happening here than has happened in all the previous exercises. All right, so notice that here, my x values are approaching 4, but I'm getting different results here. For the outputs are not approaching a single value. They're approaching different values depending on which side we're on. In a situation like this, right, these are approaching different numbers, right? When this happens, we say this limit does not exist. So if we're approaching from the left and approaching from the right, and we're getting different outputs depending on the direction we approach from, we say the limit does not exist. It's not undefined. That means something different to me. An undefined expression means like we're dividing by 0. That's an undefined expression. This is not the same. We say does not exist. All right, now here, this next example, we have the limit with x approaching 3 of the function, where the function is defined piecewise, right? We've got these two different pieces. We have x minus 3 squared plus 4 if x is less than 3, and 2x minus 2 if x is greater than 3. So here we've got to be careful about this. If we're going to use our calculator, we have to kind of break this up into two problems. So let's just look at the first piece. What if we had x minus 3 squared plus 4? But now this is only valid if x is less than 3. All right, so if x is less than 3, we could use inputs like 2.9, 2.99, 2.999. Again, it's showing 4, but really it's 4 point and a bunch of decimal places. So let me drag this down here. Okay, so this is only the first piece, right? This is only the x minus 3 squared plus 4 if x is less than 3. So that's the first piece. Now let's consider the second piece. Now we have 2x minus 2, but this is only valid if x is greater than 3. So when we go to the table here, we got to delete this stuff. And let's see, if x is greater than 3, we could use, say, 3.1, 3.01, 3.001. All right, and again, now let's highlight this 2x minus 2 for x is greater than 3. And what I see here is, we look at these outputs. All right, these outputs are approaching 4, and these outputs are also approaching 4. So it appears that this is evidence that this limit does exist, and in fact the limit as x approaches 3 of the function appears to be equal to 4. All right, what if we wanted to find the limit with x approaching 0 of the sine of 1 over x? All right, so if x is approaching 0, let's see what happens. All right, so if go to my y equals screen and I type in sine of 1 over x. All right, let me go to my table. And if we let x approach 0, let's start from the left. Let's go from the left. Negative 0.1. All right, not too bad. Negative 0.544. All right, now negative 0.01. Negative 0.506, or 0.506. That's not so bad. Negative 0.001. Oh, that's not good. I thought maybe it was getting close to 0.5, but then it swung all the way down to negative 0.82. Okay, well, maybe it gets better if I put in some more zeros here. 0.1. 0.3. Now it's back to positive. All right, well, what if we negative 0.00001? It swung negative again. Doesn't seem to be any pattern here, right? My x is getting close to 0 on the left-hand side, right, for the negative values, but my y values don't appear to be getting close to any specific value. And in fact, they're even oscillating, right? They're going positive, then negative, then positive, then negative, then positive. They don't appear to be approaching any specific value. So what this tells me, and I don't even have to check the other side, because these numbers, these outputs, aren't getting close to a specific value. Again, this limit, right, these are not approaching a specific value. And so what's happening here is, again, this limit does not exist. And from now on, if we can abbreviate that with a DNE. Does not exist as a DNE. So let's look at this other example here. What about the limit with x approaching 0 of 1 over x squared? All right, and hey, we can start with the same table, right? We have the same inputs. Let's see what's happening. If we're getting close to 0, if we have negative 0.1, the output is 100. And then negative 0.01. Let me just drag this over here. So what's happening with these outputs? My inputs are getting closer and closer to 0. My outputs, remember this notation, 1 on this calculator, this 1E6, what that notation means is, 1 times 10 to the 6th power. That's 1,000,000. And 1 times 10 to the 8th, that's 100 million. 1 times 10 to the 10th, that's 10 billion. So what's happening here? These outputs are getting very large, right? These are becoming infinitely large. Now, they're not approaching a specific number, though. Right? The outputs are getting very large. But not approaching a specific number. So what we're going to say for now is this limit does not exist. Later on, when we discuss it a little more, we will say that this is an infinite limit. For now, we're going to say it does not exist. Later on, we'll revise this. Now, we can also see the same result as this on the other side. So if we were to put in positive numbers, 0.1, 0.01, 0.001, we see the same pattern, that the outputs are getting very, very large. And again, this would be a limit that for now does not exist. It's an infinite limit. So, if we're trying to find the limit, when will that limit not exist? There are basically 3 possibilities. There are 3 situations where a limit will not exist. All right, so first example we saw was if the function approaches different values on either side of A. So we saw that we saw this example with the absolute value function, that depending on which side of A we got different outputs, this limit would not exist. The second situation that we saw was the function oscillates or does not appear, the f of x does not approach a specific number. As x approaches A. All right. In the third case, and the other thing that we saw was that this one's sort of oscillating, right? All right, we saw an oscillating behavior, but not approaching a specific number. The third case was similar. The function did not approach a specific number. As x approaches a. But this is more of an infinite situation, right? The output grows without bound. So those are the three situations that we can have where a limit will not exist. If we approach different values, depending on which side of A we have. If we're not approaching a specific number, and we have two different sort of subcases. Either an oscillation, like the outputs kind of just jump all around, or the outputs grow very large in either a positive direction or a negative direction, just depending on what we have. Okay, so that's when a limit will not exist. Now we've been focusing so far on using tables, but we can also consider graphs, and we can evaluate limits based on a graph. So let's see an example. I took this from the Paul's Notes website, and there's a link to it. I provided that link in the PDF. So here we have a graph of a function. For each of the given points, determine the value of f of a. All right, so what's the function evaluated at a? And the limit as x approaches a of the function. If any of the quantities do not exist, please explain why. All right, so let's take a look at this. If a is negative 2, all right, so if a is negative 2, we're asked two things. What's f of negative 2? And what's the limit as x approaches negative 2 of the function? All right, so f of negative 2. Just reading the graph, we've known how to do this since like algebra. This is saying the input is negative 2. What's the output? If the input is negative 2, the output is, we go to the solid point, the output is 2. Now, the limit of the function as x approaches negative 2. What's happening to the function as we get close to negative 2 on either side? As we get close to negative 2 on the left, the outputs appear to be getting closer to 4. As we approach negative 2 from the right, the outputs appear to be getting closer to 4. So the limit as x approaches negative 2 of the function is 4. All right, now if a is negative 1, f of negative 1, and the limit as x approaches negative 1 of f of x. Let's see, f of negative 1. If my input is negative 1, my output is negative 3. Now, as I get close to negative 1, well, if I come in from the left-hand side, the outputs appear to be getting close to 1. But if I come in from the right-hand side, the outputs appear to be getting closer and closer to negative 3. So this limit does not exist. On either side, we're approaching different values. Let's see about purple. All right, so purple. If a is 2, f of 2, and the limit with x approaching 2 of f of x. F of 2 is negative 1. Now, as I approach 2 from the left, the outputs appear to be approaching negative 1. But if I approach 2 from the right, the outputs appear to be approaching positive 2. This limit does not exist. Again, different values. All right, and finally, if a is 3, let's see, f of 3. If my input is 3, the output appears to be 5. And finding the limit with x approaching 3. Let's see, if I move in from the left, the output appears to be getting close to 5. As I move in from the right, the output appears to be getting close to 5 as well. This limit is also equal to 5. Okay. All right, so here's another similar exercise. Now would be a great time to pause. Try this one out on your own. All right, so hopefully you've tried this one out on your own. Let's take a look at it. All right, so again, here we have a graph of a function, and we're given some a values. All right, so if a is -3, let's see, what is f of -3? F of -3, if my input is -3, the output appears to be 5. The limit with x approaching -3 of the function. All right, so here's what I see. If I approach -3 from the left, my outputs are becoming very large negative numbers. Now, if I'm approaching 3 from the right, -3 from the right, I get a nice value, right? It appears to be getting close to 5. Again, these aren't the same on the left and the right, and we have that infinite, it's growing without bound as x approaches -3 from the left. So this limit does not exist. All right, if a is -1, then f of -1, let's see. If my input is -1, there is no solid point for me to go to. So what we would say is f of -1 is undefined. All right, the function is not defined when the input is -1. Now the limit is defined. All right, the limit as x approaches -1 of the function. As I get close to -1 on the left and the right, the outputs get closer and closer to 3. All right, if a is 1, f of 1, if my input is 1, the output going to the solid point appears to be -2. The limit with x approaching 1 of the function. If I come in from the left, the outputs appear to be getting close to 1. But if I come in from the right, the outputs get close to -2. This limit does not exist. And finally, if a is 3, this is actually the easy one. Notice that if my input is 3, I can go directly to the point at 2. And as I come in from the left and from the right, it is approaching that same value. So I would say f of 3 is 2, and the limit with x approaching 3 of the function is also 2. All right, so that concludes this topic on the introduction to limits. In the next topic, what we'll do is we'll talk more about what's happening on the left and the right, what we call one-sided limits. All right, so thank you for watching. Have a great day.